All right. So with the real world environment, what we have to do is we have to come up with these Q values or the best possible Q value, the best possible action to take. And in real world problems, just because the state of the world basically is non-deterministic, it's continuous, the state space is infinite, you can just take multiple actions. Applying just Q learning is not just it's not just straightforward. What you will have to do is, in that case, so I'm gonna go over very briefly this Q learning algorithm. And instead of this max, what we will have to do is we actually, so these are a few examples that I trained. We actually, estimate the Q values. And you will see where these functions come from and where are these, weights that we can calculate. And that's basically a very famous technique using neural networks. And we will go over. Actually, we will learn that. So I'll just show you in just a few minutes. Okay. So what I'm going to show is actually the deep Q network, using a deep neural network to train the Q values. So we're not going to be told, all right? And these weights are actually going to be learned. All right, so we'll see that in just a few moments. Let me draw a few things before we start with our examples. So what we did before was we said that we actually have a I'm trying to write and it's not writing. Okay, I'm going to share the screen again. Oh, it was actually drawing, but we said before that we have a state space, right? And we have the action space that is known. That is for deterministic environments. In most real world scenarios, we actually don't have information about that. So how do we even get the Q values in that case? So that becomes a little tricky. So what you do is, in that case, you actually have provide inputs, x1 all the way up to xn, and that is your input and possible states that your agent or robot can be in. You actually train a deep neural network with hidden layers, and you learn the actions based on the weights. It's too many, something like this. Okay, I'll just draw and it will be messy, but I hope you get the idea. So we have the input, these all are connected with each of the neuron or nodes. Okay, so what we have is we have input that is known, and we don't know about the actions. What is the best action that we that we have to take? Okay, so in that case, we actually just learn the actions based on just a deep neural network. So we actually identify those weights, we learn those weights based on different functions. So each neuron actually has a function, okay? Has a function behind it based on the equation that I just mentioned. I'll explain that in just a few minutes. But the idea is, instead of having that long equation, you actually learn the actions or the Q values based on the neural network. So every single time you are in a specific state, that is going to be identified by the input. That input is provided to a deep neural network. The neural network basically gets trained, updates its weights accordingly, and then gives us what is the best possible action to take if you are in a specific state. And how does that improve? How do the weights improve? By having multiple examples, multiple samples that you observe. All right. So, like for example, you say like with a robot, I took an action, right? So I provide that as an input to my deep neural network. Okay, deep neural network, it will basically be a bunch of numbers, states, right? Maybe it's an XY position. It's an XY position of your robot, right? It does look so messy. Yes, I can. So basically, these are all just the connections that are. Where do they connect? Yeah, so it's a flow from left to right. So all the inputs are connected with all the hidden layer neurons. I'll tell you in week 12 what the neural network is and what the neurons are and what these connections are. Okay. So which I know. So these, you have the input as states, okay? You're basically, you have the inputs as states, and you provide that as input to your neural network. Neural network will actually do some crunching and do some numbering, and also learn all these weights of these arcs, right? Just like probabilities that we have been talking about with the arcs. Don't worry about it, because I have a detailed lecture on deep neural networks or on neural networks, how these weights are trained in the coming weeks. But the idea behind this is that initially we just don't know the actions. And after crunching the numbers and running a neural network, training a neural network by providing multiple samples as an input to this, it will give us the action. It will give us the possible actions, the probabilities. So in one possible state, what are the probabilities of actions that you can? Because initially you don't have anything, because your robot or your agent hasn't learned anything about the environment, right? It is not even going to have a policy, right? A policy is what? Like in each state, where can the robot go, or what action can the robot take? For example, in a grid world, right, we saw that in each state, the robot can take either east, west, north, or south, right? But we didn't know with what probability it can go east, with what probability it can go west, north, or south, right? So this is what we are trying to learn. Like, what is the probability that it can go north? So how will it know? So we will get the input, right? And we will tell the neural network that at one point, if we take the action north, what happens? According to the neural network, our reward goes lower or our reward goes higher. So that's how the neural network updates its weights to train itself to give us the probabilities of the actions. Okay, so it's an actor, deep Q network that will give us the probabilities of actions, possible actions. So that's how we learn the Q values in our, non-deterministic space. And this is a very famous, technique that is applied. And then there are several variations of these neural networks. For example, deep deterministic policy gradient. Okay, actor critique model, advanced, which actor critique model? A3C. So it determines these actions based on the set or failure. A failure can also happen on a curve, right? A robot may fall at a certain space. So whatever the input is, whatever the current state of the robot is, it will learn the probabilities of actions, whatever happened in that state. So based on multiple samples, it will basically continue updating the probabilities of the actions. And that gives us the policy. The deep Q network, deep neural network gives us the policy, or basically the probabilities based on the actions. probabilities of the actions given that you are in a specific state, right? So here in this part, what you have is you have states, right? And you have your input variables like x1 up to xn. What do I mean by x1 up to xn? Well, these can be, let's say, your robot's motor positions, servo motors that we have, right? Like its legs, its arms, etc., etc. So every single row in this is actually one possible state that you have. And once this is given as an input in here, it learns the probabilities of the actions. So you provide multiple states after you carry out a number of samples, multiple samples, provide that an input to the deep neural network, and it gives us the possible or probabilities of actions to take. And that's what, remember, policy. You have to learn the policy, right? The probabilities of actions. Yes, our neural network is actually learning the policy. And policy gives us the transition matrix, right? The transitions, like the probabilities with which you can take a specific action. Remember, for the grid world, what we had was something like this, right? And then in each square, we had something like this, an arrow. So that was our policy, that for each state, what is the best possible action to take? Correct? Right? But you see here, I'm only just learning the probabilities of actions here, right? It's not giving me the maximum or what is the best action. So far, we just learn the probabilities of actions, or we update the policy every single time we make an observation or we run an episode, right? We update our policy. What was the feature of the temporal difference learning? Remember, we said that it's an on-policy learning algorithm that not only learns the policy every time or updates the policy every time we have an episode, but it also gives us the best value function, best Q value. Correct? So far, we have just updated the policy, but where does the best action come from? Where does the best action come from? Actually, it turns out that you can do something like this. You can get these learned actions, okay? Learn actions along with the states that you can possibly be in. And now what you're doing is you're saying, I'm in a specific state. What happens if I take a specific action? What happens if I take a specific action among these possible actions that are given, right? You actually train another neural network, another deep neural network, and give you the Q values. So now, before, you only learned about the policy. The policy gets updated. What is the probability for a certain action, all possible actions within one state that you're in, right? Is it making sense by any chance? I know that we haven't gone through the structure of the neural network that we will go over in the machine learning parts in the coming weeks, okay? Right. Yes. So our actions, probabilities of actions, or the transition matrix, the transition probabilities of certain actions becomes our policy. Our policy. Like at each state, remember, we also had something like this. So in our grid world, we said that there are 4 possible actions. If you go east, there might be 0.5 reward that you might have. If you go south, it might be 0.1, it might be 0.1, and it might be 0.3, something like that, right? So we're learning those probabilities of actions, possible actions in each possible state with one network. That's an actor network. actor network. It's an actor. So it acts and learns the policy. But now we need the Q values. Now we need the best possible action. What is the best possible action to take so that we can draw the arrows on the policy, right? To do that, we provide this, the learned actions and the state together and learn another deep neural network to give us the Q values, the best possible action, because now we have information about the actions and also we have the information about the states. We can combine them together, learn a new neural network, and actually get the Q values. So actions is as so from a grid board, an XY position where you can be for a robot, or suppose that the antropod, right? It actually has a specific XY position, physical position where it is. That's a possible state. Different, or for a vehicle, for a self-driving vehicle, it may have a latitude, longitude value, a specific position on the map. Exactly, that's an action.
State.
Correct.
So action states.
Actions would lead to new states. Exactly. So now we know the probabilities of actions, right? We also need to know where would a specific action lead us and what is the best action we should take. So we combine the actions together with the states, train a new deep neural network, and actually get the Q values, the best possible value.
So that would be like the probability of the actions.
Yes, right. Okay, so in terms of the code, I'll go over a very brief example of the code so that it makes sense. It makes sense what I am talking about. Where do I have the code open? All right. I'm gonna switch over to my laptop mode so that I can show you guys that the code. Oh. Here, and here again. And here is the temporal difference learning code for Anthrobot. What it does is, if you see, we're gonna go over an actor network that gives us, so here, basically MLP, it comes from this function. Okay, I'm not gonna go over each line of the code because we have several sessions that we will have in our coming weeks. But the idea basically is that you have an actor network that will learn the policy, return the actions, okay, the probabilities of the actions, and then you will have the critique network that will give us the max function, okay. It's hard to trace where, so self.max action, okay. Okay, so this is for critique state action. Okay, let me just start because it might be super confusing, but what the idea is, basically you have an actor deep neural network that learns the actions, and then you provide the actions and state, and there's another neural network that gives you the maximum Q value.
So temporal difference is a form of deep learning.
Temporal difference learning for non-deterministic environments, temporal difference learning is a full method. But what we have seen for the cardpool, last time when we were in the reinforcement learning, it's actually not the deep learning, because we never used any deep neural network, because what we did was we already simplified our environment into a deterministic environment. If your environment is non-deterministic, then your temporal difference learning can be considered as a deep learning, solution where you can implement actor and critique models. Okay, so this is what I was doing late at night till like 4 a.m. Okay, so what is it? Oh, by the way, self-driving car demo. So another example that I also had. So this is an environment, just like we said that there are multiple environments that are created, and we also used one environment in the past, that is the cardboard. And it is developed by the company, Elon Musk's company, OpenAI. It's called GYM, GYM, GYM environment. It has environments for multiple different, real world problems that you can use to solve several different problems. So this is actually another environment that is created by someone else that I just forgot. It's called Kivy, I think. Kivy. Kivy. They have designed this environment in which you can see a little cute robot car that moves within a window, right? And you actually draw obstacles around it. And what it does is every time the car basically hits that obstacle is basically some sand, okay? As soon as it gets on the sand, its reward gets lower. It will get reward in minus. So slowly as it learns using the actor and critique model, every single state, the vehicle moves one state, takes a turn, goes to a specific position and sees, am I on the sand or am I not on the sand? Okay. It will take an action by the actor model. It will give us like, okay, for a specific position that it is in, for a specific state that it is in within the environment, it will give you the probabilities of taking whatever action, or like turning left, turning 20 degrees left, turning 20 degrees right, etc., will give you the actions. And then it will see, has it hit the sand? Has it gotten on the sand or not? If it has gotten on the sand, its reward gets lower, and by lower reward and the possible actions, the critique model criticizes that action and says, don't take that next time because you have hit it, you have gotten the lower reward, therefore turn right, turn left, or don't even go into that state next time. Okay, so the critique actor model learns the policy, critique model criticizes them at every single step. So it's a really, nice example that I went over. I had deep Q network. Deep Q network. I thought this was a video. Oh. Oh, it's not gonna play a video like that? Ah, okay. So what I did was, so there's it's just an already running example that has, the map.py. So map.py, it's a reinforcement learning environment in which actor and critique model is already created. There is an environment that you can create. You can create a car, and you can draw different obstacles within the environment, and then you will see the vehicle moving or car moving in the environment. And slowly it will learn. I'll show you what learning means. So you see here, so I run map, okay? So you will see a little car that is moving in the environment, right? So what you can do is you can draw obstacles. Basically, this is the sand. So initially, in the first few attempts, it will actually hit the sand. And then slowly it will start learning that hitting the sand is not a good option. It's not a good way to move, in the environment, because you will get the lower reward. And that's what helps it learn is the critique model. Okay, so I mean, in the first attempt, you see it actually came from the sand right here. That was when it was actually in the learning process. So slowly it will start learning, and I'm trying to just, draw different obstacles around it. And the more difficult you make for it, the environment, the more difficult it becomes for it to just, navigate within the environment. And sometimes it will actually go over the sand and it will get the lower reward. All right. So the idea is now you see it just got stuck because it was thinking that I can just go, because it just gets scared of this part. And when it goes here, it will come back here and it will just keep hitting the walls, hitting the sand. I just tried to change the, the sand, also the sand structure like that. See, initially it actually tried to hit that part and now it tried to escape. It's trying to stay away from the sand as much as possible because getting on the sand gives it lower reward. Now it's stuck. No, actually I stopped. I started the simulation. So slowly, when I made it learn, this is what it did. Oh. This is what it started doing after. We'll just try to stay away from the sand because now its Q values are learned using the deep Q network, telling it that, okay, getting closer to the sand is not a good idea. Just stay away from it. And it will just move around, staying away from the sand. Okay, so that's basically the actor critique model. You run several episodes, you let the actor learn the policy, and then you let the critique criticize the policy and improve upon the policy every single episode that you have. I think, this is the Atari game that I trained on my computer, last night. And that's once again a deep Q network, actor and critique model. And I'll tell you the reason why I had to train the actor and critique model. So it gets pretty fast. It's a, GIF image, and then we'll just keep running. So what happens is you see every single, image, every single image is actually a state. Is a state for this environment, right? So like every position of your, I don't know, whatever you call it, and then the pixel value is actually a possible state. So it's a non-deterministic environment in which you cannot, even if you try to make a deterministic environment, it's just so many different possibilities. So what we do is for every different state, it actually learns what happened the last time if you were like away from the dot, what happened? Your reward was pretty lower. So actor was trying to learn the policy where to get, and then the critique model criticizes the actor and tells the actor model to just move it into the according, location, according XY position, so that your policy gets improved every single time you run this episode. So there are 289 episodes. No, this is the score actually. So I learned based on 3,300 different episodes, and 3,300 episodes of, like every single, image with these specific XY positions of this dot and the stand thing, it's a state. It's a possible state.
So it was going fast.
Oh yeah, it actually trained for more than an hour. Because my computer is not that strong. So we had a deep, convolutional neural network, not deep neural network, not only just deep neural network. I trained a deep convolutional neural network to train this Atari game to learn where to position this to win the game. That's once again the actor and critique model. This is something funny that I spent a lot of time. So what happened was with the ant robot, I'll just play it. So there are several windows that I had open. I have a robot on one end, and I have the AR pants. So what happens is with this ant robot, you have to basically calibrate the camera. So you have a webcam that is looking at these AR tags and these tags. You first have to calibrate and let the camera know to always find these AR tags within the image So it continuously gets the frames, 60 frames per second, which is pretty fast, right? Within each frame, it recognizes where the AR tags are here and here, and then it actually looks at the position of this AR tag, and then it looks at what is the distance between these two. And the larger the distance, the lower the reward. The smaller the distance, shorter the distance, the higher the reward. So slowly, after multiple episodes, the temporal difference learning, actor critique, actor basically will say, okay, here's my policy. So here's where the robot stands right now, and here are the servo, these motor, positions are, their velocities, in which direction they're moving, et cetera, et cetera. That's the state space, right? And it says that, okay, from this position, this is the next possible state that I can have. Meaning, possible state means that the positions or velocities of these servo motors, and there can be multiple combinations, right? So at a specific position, one servo motor can move in one certain direction at a certain velocity, right? And it's a non-deterministic environment because your servo motors can have any, velocity at any different position in any different angle, right? So the actor learns that in this specific position, there are specific movements that I can make. So that's the probabilities of the actions. That's the actor network will give us the actions, right? And then the critique model takes that input and says, based on these states and these positions of the servo motors, and based on the distance, the next action that you're going to take is going to be either the best action or not the best action or not a better action. It might just move you away from this AR tag, right? So the critique every time gives us the possible actions that will actually move this robot closer to those AR tags. So at every episode that you have, it actually tries to minimize the distance between the robot and the AR tags board. And after several episodes, it will actually learn what are the best possible positions and how to move them in a certain direction to get closer to that board as fast as possible. So those are the actor and critique models that are actually working together. But I figured out that it was not as simple as I thought of. So you have to run basically the server so there are two different programs that are running behind. So you have to run the server and then you have to run the proxy also. Server and proxy will have to run at the same time. And then there is a server basically that takes the frames, that takes the images, and then the train client, another Python file that learns what are the positions, identifies the tag. So I'm going to play this video. So I'm going to do the task walk. Is this the old one? Maybe. So you see here, these AR tags are actually identified by the program that is called show Aruka board. So show board, as soon as you run the program show board, the board will be shown in the frames and it will recognize these AR tags, this one and these ones on the camera. And then it will show you, what is the X, Y position of the robot, what is the pitch, what is the exposure, et cetera, all those, the frame features, frame properties that it will have. And running an episode was actually very difficult. I don't know if you can see the volume. So even after, so these were, I think, a few of the very first episodes. So it just gets stuck, right? So every time it gets stuck, I have to stop the program, I have to run it again, and then run the train client again to let it know that, you got stuck, continue with your episode. So I'm going to try to, run it today to hopefully see if the frame or the image quality is better. So now we see it actually identifies. So the moment it the moment it fails to detect those AR tags, the program will get stuck. Will say, oh, I cannot find the AR tag. I cannot find the robot within the frame, and it will just stop. So slowly, and that's when my phone dropped from my hand. I think there was one episode that was actually pretty long. Okay, it got stuck again. So it was actually very, very annoying process last night. Oops. Oh, it doesn't get forward. So I tried to run multiple examples, but there was not enough light at that time, late at night. So I was only able to get only 9 episodes. I wish there was some sound also that I could show you guys, but I wanna just do this, okay? Run this example and see what it does right now. So let me show you guys this quickly, and then we will stop. If the I mean, at nighttime it was, the video quality was not that great. Oh, okay. It is running. So let me bring it over. So right now it's running, and all what I will have to do is to run rollout server. Yeah. Where is rollout? No, not rollout server. Train client. So I'm gonna run this file with train client, and let's see what happens. Come on, come on. It is live right now. It is running live in my home office right now. Got stuck. Okay, 1 episode finished. You see? So now it is actually episode 11. So not bad. I wish I had the window curtains open so that there could have been enough light. Because I was working really late last night, so I turned the curtains down, put the curtains down. Yeah, this is actually a flag position that it gets reset. So it's unable to do that, you have to stop the programs and rerun it again. When you rerun the program, it will get back to its, this flag position once again. So right now it's actually creating an Actor Critique episode model that it can take those weights from the previous episodes and continue. Yes. Yeah, you see here? So it says result resuming from 11, and it says return. As soon as you get the return, yeah, the episode is finished. And when you go to the folder that is, where is it? And if you go to this, is this stand or what? So you see here, it actually creates a new set of weights. So remember I said that there are multiple links in the Q network, in the deep neural network. So this file, it says _10 pickle. It actually gives you the weights of all those arcs, all those links. Okay, now it's stopped. It got stuck. So I'll have to, so you see here, it says stuck, quitting. Yeah, it is quitting. So what I have to do in that case is, I have to go to that file, do Control-C, all right, run the program again, come back to my Spider, stop, restart the kernel. and then run this train client again. But I can see the video quality is still not that great in my train client. So what happens is this rollout server, it enables the video, it gets the video input, the positions and positions of AR tags, and then the train client continuously communicates with the rollout server to get these, the positions, XY positions of these AR tags, and then it learns the actor and critique model. So it's actually divided into two different programs, just for convenience. There's no, other logical reasoning behind. So you see here, it just started again, but it's gonna get stuck because the video quality is not that great. So it was actually a very interesting but kind of annoying exercise last night. It made me stay awake till really late last night. I was up till 4 a.m. I slept around like 4:15, and then my son woke me up at 6 a.m. 6:15. He doesn't like to sleep in the crib. He likes to sleep with me, and then he starts robot. And this is it will look like. This is after complete training, by the way. So you will not see the examples where it falls down and it just, all the episodes where it falls down and is not able to train. But after the training, it will do something. Okay, not so bad. So you see here, what they did is they tried to replicate, these joints. Behind this gym environment, these joints are actually the servo motors. The motors which can have a velocity and it can have a specific angle, et cetera, et cetera. So what they did is they actually took the idea from there and converted it into a real world, robot. Sorry? You don't think we have? So with this robot, if you see, so it has this that can go up and down, okay? And then it has this joint, where is it? Then it has this joint that can go left, right. Okay, so one for left, right, and one for up, down. So for up and down, it helps it stand and gets it like into a certain position. And then left, right, it helps you to just actually move, make a move. Okay. It looks more like a spider, to be honest, than an ant. Right. It will actually make all sorts of actions, and then we'll learn what are the best actions. What is the best action to take for each possible state that it is running? Yeah, it's not. It's only 9 episodes. Based on only 9 episodes, it's not going to learn much. One thing that the last thing that I wanted to mention, that I found this link that has several very interesting environments that are for reinforcement learning. I strongly suggest if you can go to that link. I will upload this slide. I'll upload this PowerPoint on Canvas today. I highly recommend if you go over, this web page, because they provide 15 different reinforcement learning environments. Some for gaming, some for healthcare, some for robotics. Some of those might be really interesting for you guys. All what you will have to do is you take one specific environment that you would really like to work in, let's say gaming. You really like, designing a new game or something, right? Or you design a new robot that delivers the medicine to the wards, right? To the patients. Or you design a robot for the campus that actually delivers books to different, to different rooms or to lecture halls or something, or that delivers food. There is I don't know what robotic company that actually is at UCLA. You go to UCLA, you will see robots moving all over the place, everywhere. they actually deliver food to student dorms and offices. So what you do is that company, you place an order online, they put it in the robot with, like nice hot food, and then just they let the robot go. What they do have is they have a complete map. The robot has a complete map of the campus. And then when the customer or the client places an order, it tells the latitude, longitude, it tells the location or position on the map where the food should be delivered. And then the robot finds its own way to go deliver the food. So I would say highly recommend, strongly recommend you just look at some of these environments and see what is, what is something that is really interesting. Oh, by the way, there is another more advanced ant environment that was designed by Muhoko. I don't know, Mujoko or Muhoko, whatever. I'm not sure. I may be pronouncing it, wrong. There's a scheduling, problem that is solved using reinforcement learning. Not sure what this is for. Oh yeah, Rexin. Yeah. Then there's a reinforcement learning card games. Not sure how many of you like to go to a casino and play blackjack. Play blackjack. So there's the guy at DeepMind. He was actually a co-founder of DeepMind. DeepMind is acquired by Google. One of the pioneers in reinforcement learning. The guy named David Silver. He did his PhD from Toronto. From his advisor was, I forgot his name. He basically has been working in the field of reinforcement learning since the 90s. And this SARSA, temporal difference learning, actually, he wrote a book with it, which is one of the most popular books in reinforcement learning that he did his PhD in. And he was the one behind designing the game of Go. If you remember in lecture 1, we went over the game of Go that actually beat the world champion. So he was behind that. He was the mastermind behind that. Along with him, some of the co-authors actually provided a reinforcement learning solution to the blackjack. So they ran I think hundreds of thousands of different simulations of blackjack. And they proposed a solution and said that if who's the person called who actually draws the cards? I don't know what, dealer, basically. They gave a map of reinforcement learning card games or blackjack. They gave a map. They said that if a dealer has a card, like let's say 2 or ace or jack or 10, whatever, what is the best possible move for you to become a millionaire? But they don't take the responsibility. They say, if you lose, it's not our responsibility. But this is the best possible, action space that they came up with after running hundreds of thousands of different simulations and designed a blackjack. So, who knows? If you take that small figure or a map that they have designed, and every time the dealer does something, you just look at the map and say, okay, I'm gonna keep it, or I'm gonna just draw, or and maybe just win some money. So they designed a blackjack game. Not sure what this is, but economics. In economics, they have designed an environment, basically kind of a game-like environment. There are some that are really interesting. Remember the grid world? So they also designed a grid world for reinforcement learning. Okay, multiple agent grid world, self-driving car. I think that might be very interesting for you to check. The good thing about this is, as long as you have the idea, of what problem you want to solve, the actor critique and this pure learning and everything is just exactly the same. The technique or the algorithm is exactly the same behind multiple different, problems. All what you will have to do in your programs is change the state space to your state space and change the action space to your action space. That is it. Rest of the programs, even I can provide you those programs. The temporal difference learning or Q learning or even deep Q networks. I can provide you those programs. You just have to change the state space and action space and come up with something really interesting, really, really impressive product. ahead of himself. So you see here, this is your car, and you see these projections. This is where the car can actually see at each step, at each point in time. So you see here, this is your XY position, and then these are the views that you can have at every single step in time. And then after that, that these state space, your XY position, your speed, the road structure, etc., that is all your state space. And then you can learn an accurate critique model of what is the best action to take at this point. Slow down, stop, keep going. If the traffic light is green, turn right, if you have to turn right. So you can design your own accurate critique model to help us to have a self-driving car in a much more busy environment. I don't think even Tesla can work in this kind of environment yet. So you can even design, like, in all honesty, you can even design an algorithm, an accurate critique model that can be a blockbuster for a Tesla model. Because I can tell you there have been a few occasions where I really got scared with by my Tesla fully self-driving. Even today, when I was coming today, so there was a truck that was in the right lane, and my Tesla was going, I think, at 80, 78, something like that. The truck actually changed the lane, and Tesla thought that it's coming into my lane. It just like braked like really, really fast, and it made a really nice, not really loud sound, and I really got scared. It's because the self-driving, feature of Tesla is not at that level yet, where it can be at a human level. You can design some simulation like this and train a model that is much more improved model and sell it to Tesla. Even a busier environment that you can have. Not sure what this is. So I'm going to share. Sorry. I don't look like you have. Yeah. So this is just a simulation, but the idea behind this entire thing is just the same. So what I'm going to say is,